Here, do you want to design your own machines? Chances are you need gears to make your machine work. Join me as I explain how to design Involute Spur gears and mesh them like this. And finally, make your own machine such as this mechanical pendulum clock. Let's have a quick discussion on Involute Spur gear terminologies. First, I want to introduce the constant parameters. Number one is the module. The module determines the size of the gear tooth and has values that range from 1 to 50. In a set of gears that are shown here, you could see that the tooth size as well as the gear size increase as the value of the module increases. So we could say that the module determines how big the gear is. The bigger its value, the bigger the tooth profile. This set of gears here have numbers of teeth 20 and 30 respectively. Their module increased from 1 to 5. You could see that the gear size also increase as the values of the module increase. Next is the pressure angle. It is the angle between the line of action and the pitch line. For the two meshed gears here, the pitch line is this one and the line of action is the red line. The pressure angle is the inclination of the line of action from the pitch line. Let's get a closer look at the pressure angle and the line of action. Suppose we have two wheels that rotate at shafts A and B respectively and have contact point at point P. As wheel 1 rotates clockwise, wheel 2 also rotates in the opposite direction due to the frictional force exerted by wheel 1 on wheel 2 at contact P. We call this force F1 and is tangent to wheel 1 and wheel 2. When there is no sliding effect between wheel 1 and wheel 2, we could say that wheel 1 has exerted the maximum force F1 to wheel 2 and that the torque or work done on wheel 2 is also maximum. Suppose we have another force F2 that has the same magnitude as that of F1 and is introduced at an angle theta like what is shown here. The x and y components of force F2 are Fx and Fy respectively. Fx doesn't do anything useful to wheel 2 because its direction intersects the shaft of wheel 2. We say that the torque done by Fx is equal to 0. The y component Fy, however, is the only force that rotates the wheel 2 and its magnitude is equal to F2 times the cosine of the angle at which F2 is introduced, in this case the angle theta. If we place F1 and F2 side by side and assume that their values are equal, then graphically their lengths or magnitudes are also equal. However, due to the angle of action done by F2, the torque it acts on wheel 2 has decreased. In this case, the only useful force exerted by F2 is its y component, Fy. If we compare the three forces together, F1, F2 and Fy, it is clear that Fy has a lesser magnitude based on its length. The torque is defined as the force times the distance from the fulcrum. Then, we could say that the torque done by F1 is greater than the torque done by Fy. Besides, the angle theta is indirectly proportional to the torque and on wheel 2. That is, the bigger the angle becomes, the lesser the torque. Now let's go back to the spur gear diagram. Again, this is the pitch line, the line of action, and the pressure angle. The force that we mentioned will lie on the line of action. It means that its direction will also be parallel to the line of action. The contact between the two gears falls along the line of action. That means, as the gears rotate, the teeth of the gears will always meet along the line of action. To explain further, let's view an animation from techscience.com. Here we have the brown gear driving the blue gear. The contact points between them are traced as the gears rotate. It is clear that they always be in contact along the line of action. As mentioned before, the y component of the force will create torque on the driven gear, thus rotating it accordingly. The x component, Fx, is insignificant in the system and will be transformed into heat and noise as a result of friction. As we increase the pressure angle, the y component decreases while the x component increases, resulting in less torque and more friction. So can we say that it's better to minimize the pressure angle? We have discussed the effects of the pressure angle on the forces of the two gears. Now let's talk about how the involute profile of the gears change as we vary the pressure angle. In the illustration shown, we have three sets of gears with similar modules and number of teeth. The white, yellow, and green gears have pressure angles of 14.5, 20, and 25 respectively. If we take a closer look, there is a slight difference in the gear profile. As we zoom in a bit more and overlap the gears, the difference in the tooth profile has become more obvious. The base of the gear tooth with a 14.5 pressure angle is narrower compared to the gears with higher angles. However, its tip is wider than other gears. As the base of the tooth profile of high pressure angles is wider, it can withstand more shear force compared to that of profiles with less pressure angle. Aside from its strength, meshing gears with high pressure angle have less tendency to have interference because of their narrow tip. We could summarize the advantage and disadvantages of having a high and low pressure angle. For a high pressure angle, the advantages are strong, it has high shear strength, eliminates interference between gears. Disadvantages: less efficient, noisy, and heats up at high RPM. For gears with less pressure angles, the advantages are less friction, minimum noise and heat, and more efficient. Disadvantages: weak, less shear strength, interference at high gear ratio, and needs undercutting. The next parameter that I want to talk about is the number of teeth of the gear, or N. Similar to the module, the number of teeth determines the size of the gear. It is also used to get the gear ratio of the paired gears. A quick background on gear ratio. Let me show you the effect of the number of teeth of the gear to its gear ratio and ultimately the angular velocity of the gears. Here, the pinion or G1 of the gear train has N of 15, or the number of teeth is 15, while the driven gear G2 has 30, or double the quantity of G1. The gear ratio of this gear train is N2 over N1, or 30 over 15, which is equal to 2. If, for example, the pinion gear has an angular velocity of 10 revolutions per minute clockwise, the driven gear will have 5 revolutions per minute in the opposite direction. On the next gear train, the pinion and the driven gears have 20 and 50 teeth respectively, so the gear ratio is 50 over 20 equals 2.5. Once again, for example, if the pinion has an angular velocity of 5 rpm, the driven gear will have 5 over 2.5 or 2 rpm in the opposite direction. Those are the three important quantities that make up the size, gear ratio, and profile of the gear. The other basic terminologies of the spur gear can be derived from the three constants that we have just covered. For example, the addendum of the gear, which is described as the length of the tip of the gear to the pitch circle, is equal to 1 times the module. The addendum, on the other hand, is 1.25 times the module. This is the length of the gear tooth measured from the pitch circle to the root circle. Now let's talk about the four circles that make up the spur gear. The pitch circle. This is the pitch circle of this gear, and this is the pitch circle of this gear. The pitch circles are imaginary circles of the gears that intersect at the pitch point of the two meshed gears. In our previous example, the pitch circles of the gears are represented by wheel 1 and wheel 2. The pitch circles can be calculated by multiplying the number of teeth n and the module, or dp is equal to n times m. The base circle. This is the base circle right here. The involute profile of the tooth starts from the base circle. The diameter of the base circle can be determined mathematically by the equation dB equals dP times the cosine of the pressure angle. Geometrically, the radius of the base circle is the perpendicular distance from the center of the gear to the line of action. For this gear, the radius of the base circle can be geometrically determined by making a line from the center of the gear and perpendicular to the line of action. So this will now be our base circle for this gear. The tip circle or outer circle. It is a circle of the outermost point of the gear. Its radius is the sum of the pitch circle and the addendum. So from this pitch circle, the radius of the outer circle will be the sum of the pitch circle radius plus and the addendum. Finally, the root circle. The root circle is the circle at the base of the tooth. Its radius is the difference between the radius of the pitch circle and the addendum, B. We also have the circular pitch or CP, which is equal to pi times the ratio of the pitch circle diameter and the number of teeth. Graphically, this is the arc from the edge of the gear to the same edge of the adjacent gear, measured on the pitch circle. The circular thickness is measured on both sides of the gear on the pitch circle. It can be determined by the equation Ct equals m times pi over 2. Now that we have defined the basic terminologies of the gear and covered a little background of the involute spur gears, let us try to calculate all the parameters that we discussed. Suppose we have this gear train. The module of the gears is 5, and the pressure angle is 14.5. The pinion has 18 teeth, while the driven gear has 40 teeth. The angular speed of the pinion is 100 rpm. To solve for the addendum, we say that A is equal to 1 times 5, which is equal to 5. The addendum will be 1.25 times 5, which is equal to 6.25. After getting the addendum and addendum, we can now solve for the pitch circle diameter, which for this gear number 1, the pitch circle will be the number of teeth 18 times 5 module. This one is equal to 90. The base circle is equal to the pitch circle diameter times the cosine of the pressure angle, which is 14.5. This is approximately 87.13 mm. Now we also solve for the outer diameter, which is equal to the pitch diameter plus twice the addendum, which is 10, and this will be equal to 100. Now for the CP, or circular pitch, this is equal to pi, which is 3.14 times the pitch circle diameter of 90 divided by 18, and this will be equal to approximately 15.71. And the circular thickness would be the module 5 times 3.14 over 2. This will be equal to 7.85 mm. For the driven gear, the addendum and the addendum will be equal to the pinion gear. This will be 5, and this is equal to 6.25. Then the pitch circle diameter would be 40 times the module, which is equal to 200. Then the base circle diameter would be 200 times the cosine of 14.5. This is equal to approximately 193.63. Then we will solve for the root circle diameter, which is equal to 200 minus twice the addendum, 6.25, which is equal to 187.5 mm. The outer diameter is equal to the pitch circle diameter of 200 plus twice the addendum of 5, which is equal to 10, and this will be 210. For the circular pitch, again, this is equal to pi, which is 3.14 times the ratio of the pitch circle diameter and the number of teeth. So this is equal to approximately 15.7, the same as the previous gear. And we can also say that the circular thickness of the driven gear is equal to the circular thickness of the pinion gear. I think I missed out the root circle diameter of the pinion gear, which is equal to 90 minus twice the addendum. This is equal to 77.5. Now that we have solved all the parameters, let's solve for the gear ratio. Gear ratio is defined as the number of teeth of the driven gear over the number of teeth of the pinion gear, and this is approximately 2.22 or 2/29. And if the angular speed of the pinion gear is 100 rpm, we divide it by the gear ratio, which is 2.22. I mean 2 and 2.22. Let's just say it's 2.22. This will be equal to 45 rpm. To check whether we have come up with the correct values here, let's start with this pinion gear. We solved for the DP here, and its DP is around 90. So for example, this is the DP of the pinion gear, and the DP of the driven gear is 200. The outer diameter of the gear should have a value of 100, as we have solved here, DO, and the DO of the driven gear is 210, which is correct. The root circle will be this diameter 78, and this diameter 188. Root circle, okay, and 188. Let me adjust the precision of this parameter. Decimal. Okay, now it's showing 187.5 diameter, and this is now 77.5. So if the green circles are the pitch circles of the spur gears, and the red line is the line of action, the base circle, I mean the radius of the base circle, will be the line from the center of the gear to the line of action. I mean perpendicular to the line of action. This would now be our base circle from here to here. So if we measure this, it has a dimension of 87, which is what we calculated before, 87.13. If we increase the precision of this, it will be the same as the one that we have calculated. Similarly, for the big gear, the base circle radius can be determined by creating a line perpendicular to the line of action from the center of the gear. So if we create a circle to that line, this should become now our base circle. It has a diameter of 194. If we increase the precision here, 193.63, which is equal to what we have solved. Now we have covered how to calculate the basic parameters of the gear and also the gear ratio and the RPM.